Okay, thank you, Mr. Chairman, for the presentation, the introduction. Okay, the title of my talk is Microstructure, Distortion, and Residual Stress Investigation of Bio-Inspired Welding Partners. My talk is organized in this way. This is the outline. I will start with the introduction and motivation. Then I will speak about materials and methods, results and discussion, finally, as always, the conclusion. Let's talk about the introduction motivation. This idea came from nature. If we can see in this picture, when nature tried to join two surface, it uses a non-linear pattern, as you can see, for instance, in these cranial sutures. So the idea is to imitate nature and to investigate the effect of a sort of bio-inspired or a zigzag welding path on the performances of the joints that we obtained. In particular, in this work, we focused on the residual stresses and distortion. It is sure that by modifying the welding path, we modify the thermal and mechanical history of the points that are very close to the material that we need to weld. So we are confident that by using a different path, we can modify the residual stress distribution and also the distortion that we obtain, compared, of course, to the standard butt joint that uses a straight path. So the goal is to assess by experiment in this work the effect of a zigzag welding path on the residual stress and distortion induced by welding, this kind of welding, and compare to a standard method that uses a straight path during butt welding. So let's talk about materials and methods. Material used was a stainless steel, an austenitic stainless steel 304. The geometry is a plate of 2 millimeter thick and 300 millimeter long and 100 millimeter wide or large. They were butt welded by using laser technology, and the parameter of the laser welding are collected in this table, as you can see here, for your convenience if you want to know the specific values that we used. And the parameter were kept constant in two kind of welding. The standard that we use as a reference and the zigzag laser welding path. Capping condition is shown in this picture, and you can see that we use the table with rulers. Moreover, we have here an image that shows details about the geometric parameter of the zigzag welding paths that we used. About the residual stresses and methods, we use XRD measurements, XRD residual stress measurement. Parameters used in XRD measurement are given in this table. This is the facility that we use, the portable residual stress analyzer. And in the picture at your right, you can see the different points where the residual stresses were measured. And in particular also, you can see the components of the residual stresses. This is the longitudinal residual stress that is parallel to the welding line, and the transversal component of residual stress that is, of course, perpendicular to the welding line. You can note that for standard welding, we consider only one side, supposing that is a sort of a symmetric distribution of residual stresses. So we measure only the values on one side, starting from the fusion zone. On the other hand, by the points that we use to measure the residual stress in the zigzag path welding are in the inner size and the external size of the welding line. We carried out also the distortion measurement via coordinate measurement machine with a hybrid technology. Let's say we're using both optical and tactile probe systems. There are points that we measure within this machine, this facility, were then collected and processed in MATLAB code to generate images of the deformed shape, deformed joints. Finally, we perform standard metallurgical analysis and micro hardness profiles. Let's talk about results and discussion. First of all, the microstructure and micro hardness profiles. I want to start with the micrographs of the fusion zone in the standard welding and in the zigzag laser welding path. Here you have to note that we need to select which kind of section to consider, and we consider the section here where there is the crest of the path. And if we consider this section, the resulting fusion zone is this one, and it appears larger, of course, compared to the standard laser welding path. Moreover, we have to distinguish the internal size, that is this part, and the external size, that is this part. This picture shows the micrographs of the joint obtained by using the zigzag laser welding path. I show here only this one because we didn't find differences compared to the standard welding in terms of microstructures. In particular, here you can see the microstructure of the parent metal. It's an heavy acid grains. In the fusion zone, we have a dendritic microstructure, very fine dendritic microstructures. And in the close to the fusion zone, we can see heat affected zone. We have a acid microstructure, of course. But we didn't find a big difference in size of the grain compared to the parent metal. So, in other words, the heat affected zone is very thin. About the micro hardness profiles, you can see in the red line is the micro hardness profiles coming from the weld obtained by using zigzag welding path, and the green line is the standard welding path coming from the standard welding path. You can see that in the internal side, so in this part, the micro hardness is a little bit lower compared to the micro hardness in the external size, and also lower than the micro hardness that we measured in the standard welding. This effect can be attributed to a sort of variation in the thermal flow, in the heat flow during welding. In other words, for instance, if you consider the laser source that move in this way, when the laser source reaches the point A, we can suppose that there is a sort of preheating of the zone B. And when the laser source reaches the point B, there is a post-heating in the zone A. So we can think that there is in the internal side a sort of heat accumulation that reduces the thermal gradients and have a sort of softening effect in terms of the value that of the hardness or micro hardness that we measure. About the residual stresses, the graph at the top shows the transversal distribution of residual stress, and at the bottom the longitudinal residual stress distribution. The continuous line is come from the welded obtained by using the zigzag welding path, and of course the dot line only for symmetry we plot only one side. Is the residual stress distribution coming from the standard welding method. We can observe, first of all, that there is a non-symmetric behavior for both transversal and longitudinal residual stress coming from the bio-inspired welding path. It is expected. But we also can observe that there is a reduction of residual stress compared to the standard welding, above all if you consider the longitudinal residual stress. In the case of transversal residual stress, the reduction of residual stress is only in the internal side. In the external side, we have a sort of increase of residual stress compared to the standard welding. But globally speaking, if we consider a mean value of residual stress, we can say that using this path, we can observe a reduction of the mean residual stress compared, of course, to the standard welding. About distortion, these two images show the distortion partners of obtained for the standard and zigzag laser welding path. The results are quite similar if you consider this figure. And if we consider also the cross section here at 50 millimeter far from the welding line, we have this behavior and the values of the distortion delta Z. It is quite similar in the two cases, with a little bit increment for the zigzag welding path, but the differences can be considered negligible, in my opinion. So, for the conclusion, we can say that using a bio-inspired welding path, we can modify the distribution of residual stresses. In this case, in a positive way, in the sense that we can reduce the mean values of residual stress, above all in the longitudinal direction, where that is the component of the residual stress that it is in general predominant in butt welding. If you are familiar with residual stress of butt welding joints, we can suppose that this effect is due to a sort of pre and post heating of the bead given by the welding path, but also, in my opinion, to a different local constriction induced by current metal to the fusion zone during its solidification and cooling. About distortion, we have found no differences, or differences are negligible. Regarding the result of this work, we can say that they are strongly dependent on the geometry of the path that we used. So, as a suggestion, in the next work, we can evaluate the effects of the geometry of the path on the residual stresses and distortion, but also on fatigue strain of such kind of joints. Okay, that's all for now. Thank you very much.